All right, here we are, 15.3. This is example 4, the last example. Example 4 says there's a region W which is bounded by the following curves. So we have z equals 4 minus y squared, y equals 2x, z equals 0, and x equals 0. So all three, the last three equations, y equals 2x, z equals 0, and x equals 0, they are all equations of planes. And then this first one, z equals 4 minus y squared, is technically the term is a parabolic cylinder, but basically take your parabola, z equals 4 minus y squared. It's a parabola that opens down in the yz plane. But then since there's no x in this equation, imagine just stretching that parabola in the x direction infinitely far forever. Well, in which case, we have exactly this shape. So here's the parabola, this piece right here. We can look at the legend here. It's a little bit small, but we can see z equals 4 minus y. That should not say to the first. That should be to the second power. Just notice that. Fix that. So that is what we have right there. The bottom is our z equals 0, the xy plane. The orange plane here on the back, this is in the, if you're reading off the axes, you can see here's the x-axis, here's the y-axis coming out this way, or excuse me, going this way. And the z-axis is right here, so this plane here is in the yz plane. So that's exactly the equation, x equals 0. So those are all the four surfaces. And you can see that they intersect and they kind of form this region. You know, it's on the underside of this parabolic cylinder, so if we flip it around, sort of in that little region in here, underneath here. But that's exactly the region that we have, and let's go ahead and try and figure out what that looks like as a solid. Well, here's that solid region. We can take a look at that if we rotate it. And we can see it side by side with the other region. Let me just imagine moving this around. Oops. Let's actually just get rid of that. So yeah, that is the region. I forgot I moved something. I can't go back there. That's okay. So this is that solid region. We're supposed to be doing the triple integral over this region. So what we want to be able to do here now is think about how we can describe this region in different ways, either as being vertically simple, or excuse me, z simple, x simple, or y simple. All right, so now if we look at this region here, I went ahead and I plotted a line through this region, and I gave it two parameters. So we're going to think of a vertical line here. I don't need that. We're going to, actually I do want that. We're going to think about we're going to think about a line here. So let's give it an A. So let's pick a point in the middle here. So let's say x is, let's say 0.25. So this is an x value. And the parameter b will be some y value. So let's say about 1.5, let's say. All right. So now we can see that this is right in the middle, this line here. And then we can look at that. And that line goes through the region. It pokes down right about there in the bottom. Right here it pokes through. So now we can think about what happens if we move this line. Like we could move the line increase the x value, and eventually it will leave the region. And we can think about going through like that. And we can do the same thing with the y values. Let's bring this back into the region. And let's just let the y point vary through the region. So notice here that as long as we pick an x or y value that is in our region here, notice that the line always hits this top surface first. Even if we increase the value a little bit, if it hits a surface, it's always going to hit that surface in the top. Likewise, if we flip this around, the line always pokes out through the bottom. And for the surface, this is the portion of the xy plane. So it looks like no matter where we strike this line parallel to the z-axis, no matter where we strike it in this region, it always hits the top surface, this paraboloid, or excuse me, this parabolic cylinder, z equals 4 minus y squared, and on the bottom it always hits z equals 0. And that doesn't matter where I strike this line. So because it doesn't matter where we strike this line, it's always the same surface on top and the same surface on the bottom in the same order, we would say that this region here is z-simple. Why z-simple? Because this line is parallel to the z-axis. It extends in the z direction. All right, we're going to do something similar, but in a different direction now. So what we can do here is think about, I set it up so we're now going to poke this region with lines that extend parallel to the y direction, so in this way. So let's move this point into the region. So let's give this some value. Oh, and then you can see there's that line. Let's increase the a value. There we go. I'm not going to bother moving the b parameter because the b parameter is the y value, but this line extends in the y direction, so the y value is constant on that line. Or excuse me, the y value is going to vary anyway. So it's really just the x and z value. So now, notice here that the top surface, in other words, what surface is farther in the positive y direction? So basically, if we orient this way, where the positive y-axis is coming out of the screen, then this surface right here, which is that of the parabolic cylinder, that is the top surface, or the bigger surface because it has the bigger y value, and the surface that's the lower surface that has the smaller y value is this right here, which is the portion of the plane y equals 2x. Y equals 2x. It was this one right there. And again, we can play the same game. If we move this point, right, if we vary this, maybe we increase it a little bit so it's at the tip. And we look down, ooh, a little hard to see, but it is actually still the parabolic cylinder. Its surface is the top surface, and this portion of the plane y equals 2x is the bottom surface. So that still holds true. And then we can also make maybe make the a value very small and the z value kind of big. And again, same thing. This is the top surface, this is the bottom surface. All right, now lastly, we are going to have lines that are poking through the region in the x direction. So that means the x is going to vary, so we don't have to manipulate a, we just need to manipulate b and c. So let's just pick some values here, and then we see that this line, well, let's see, the top surface, when we say top, we really mean what's the surface that has the larger value. So in this case, if we're trying to measure things or arrange things from greatest to smallest in the x direction, this surface right here, this has the larger x value because it's farther in the x direction, which is, let me zoom out for you a little bit there. See, there's the x direction going into the board. Or we can rotate things and have the x-axis a little bit more standard to what we're used to in class. The x-axis is now coming out of the board, so this surface right here, y equals 2x, is the top or bigger surface because it has the bigger x value. And then if we look at this line, it is going to poke through the very back here. Hard to see a little bit, but right there. It's going to poke through. So this plane right here is the YZ plane, so this is the plane x equals 0. So that is going to poke through the rear. So that tells us exactly how we can split up our region into the different integrals. All right, so here's my solution to this problem. I have drawings here that are correct and accurate, but a little bit harder to visualize. It's a lot easier when we actually have something like, you know, this that we can manipulate and think about. So when we did z-simple, we said the parabola was on top and the xy plane was on the bottom. So if we look at number 1 for z-simple, do you see how our z bounds are between 0 and 4 minus y squared? So that checks out. When we did x-simple, that was the last thing we just did, the most recent graph, we said that the yz plane was the smallest x value, so that has the equation x equals 0. So this is, here's dx, so this is an x integral, so we have x equals 0. And then the larger surface, or the bigger surface, was y equals 2x. But since this is a dx integral, we need to solve this for x. So we take the equation of the plane right here and solve that for x. And we exactly get 1/2 y, so that checks out. For 3, we want to consider this to be y-simple, in which case our bounds are, well, we said that the smaller surface, the inner surface, the surface with the smaller y value, was the plane y equals 2x. So since this is a, ooh, I just noticed a typo in my own notes. That needs to be corrected. dz, dx, this should be dy, then dz. Or excuse me, dy, then dx. I'll have to correct that. I guess it doesn't make any sense with having a dx here and then having x's here. That doesn't make any sense. So that's just a little typo. dy and dx need to flip on this integral here. Okay, so here we should have y equals 2x, and here we took the equation of the parabolic cylinder and we solved that for y. But when we solve this for y, we're going to get 2 halves. We're going to get the half with, let's go back down here and take a look at this. We're going to have the half where we have plus or minus, and our our y values are positive, because if we look over here, this region here only lives in the direction where y is positive, so this side, not over here. That's why I have the plus root right here. All right, so that covers how to find the inner bounds. But how do you find these remaining bounds? Well, this is a little bit harder to do, but basically what you do is you can imagine taking everything in the region and collapsing it. So, for instance, when we are looking at this shape right here, for the first integral, if we are thinking of things as z simple, what we really want to do here is collapse this region down into the xy plane. So if you can imagine just collapsing this region down. So if you view this directly above the xy plane, which I'm attempting to do, then we get a triangle, which is exactly this triangle right here. How would we find this? Well, we just want to know it's bounded above by this surface right here, and below by z equals 0. So to know what this shadow looks like, we want to basically project that surface into the xy plane. When we do that, this crosses the xy plane right here at y equals plus or minus 2. It strikes back here, and it again strikes over here. Our region is in the first octant, the first quadrant in the xy plane, so that means we only want the positive root. So that's why over here we've got that. In particular, it's why we have y equals 2 is right there. But then it's not all of y equals 2 we want, because part of it's bounded in the xy plane by this region. So what is this equation? Y equals 2x. This is the equation in the plane, but in the xy plane it is a line. So now this region here is both vertically and horizontally simple. So we can just describe this region here as we did in 15.2 and 15.1. And that gives us the bounds here. This one, if we are saying this is an x-simple region, we're going to project the solid region into the yz plane. So when we do that, let's look back over here. What do we get? Well, the yz plane means we're going to view things it's a little bit hard to get it, but directly above the x-axis. Not perfect, but what we end up getting here is when we look, it's a little bit off, right? Because the x-axis is actually coming out of the page a little bit. That's about as good as I can get, freehanding it. And you can see that that agrees with, oops, sorry, this one I mean, right there. The shape at least. Now how do we get the equations? Well, to get the equations, what we're basically saying is if we collapse this, so what's the equation of the yz plane? It's x equals 0. So we can take the equations that we have, and effectively this equation here doesn't have an x in it. So even if we set x equal to 0, we get the same thing. So that's what the trace is in the yz plane, and we're everything within that. All right. So then this region here is both vertically and horizontally simple in the YZ plane, so we can describe that using the following description. Y is between 0 and 2, and then the lower function is z equals 0, and the upper function is z equals 4 minus y squared, and that gives us our outer bounds. Now, the bottom surface is definitely the hardest one to do. In this case, we're going to project onto the xz plane. So that means y is 0. So when y is 0, we know that this equation here is just z equals 4. Okay. So if we look down here, z equals 4, if we sketch it, technically z equals 4 is just this, right? It's just that. So the projection of that cylinder onto the xz plane, let's go ahead and see here. So xz plane, we're going to do something, let's make x going that way. If we project it onto that plane, we get something like that. So we get the same shape that we have drawn right here. We get the same thing. So that's correct. But how do we describe a point in the xz plane if we know, how do we get that point? So what we're going to have to do here is we're going to have to think about, well, if we take a point x, so some point, if a point lives on this cylinder here, it lives on this parabolic cylinder, then this means that z equals 4 minus y squared. Well, the only things that live on this slice here, if we actually look at this, to live on this surface here, this edge surface, this back surface, this is the equation y equals 2x. So this means if we have an x value of x, then on this surface, if the x value is x, that means the y value must be 2x. So that's precisely why down here we have x and 2x. And then if we know what the z value is on that portion of the surface here, the z value, the very upper z value, has to be 4 minus 4x squared, because the equation of this upper boundary is z equals 4 minus y squared. And we just said that the y value is 2x, so what is 2x quantity squared? 4x squared. So this is a generic point that lives on this arc, this upper arc here. And what we're going to do is we want to project this onto the xz plane. So this means we're going to take all of these points and flatten them into this region here. And to do that, we just set all the y values equal to 0. Because y? Well, the equation of the xz plane is y equals 0. So that becomes the equation right here that we get. The issue was we needed this equation in terms of x, and that was a little bit tricky to get. Once we have that equation down, then this region is vertically and horizontally simple, and we can easily come up with this description. All right, so the main thing here that I do want to highlight before I leave is that here the differentials I have are wrong. This should be dy, and then dx should be at the end. All right, thank you.